So today I'm going to start Galois theory, one of the most important topic of abstract algebra. And for that purpose, I'm going to start with basics of group theory, some basic idea about group theory, what is group, and what are some important notions of group theory. So for that purpose, firstly I'm defining what is group. A group is a non-empty set with an operation satisfying these four properties: closure, identity, inverse, and associative. If order of group is finite, then we say that G is a finite group, and in that case, G has finite number of element. Order of a least possible integer n such that a to power n equals a. Now after that, I am defining homomorphism of a group. Suppose phi is my which sends elements of G to G prime is a function such that phi of AB equals phi into phi B. In that case, this phi is said to be homomorphism. And here the operation between A and B is same as the operation of G, and operation between phi and phi B is same as the operation of G prime. After that, I am talking about isomorphism. What is isomorphism? Isomorphism is nothing but homomorphism which admits inverse homomorphism. That is, every element has respective inverse. That is homomorphism plus inverse means what? The function should be 1, 1 and 2. That is bijective. So homomorphism plus bijective is nothing but isomorphism. After that, I am talking about suppose we have been given order of group, and then we'll see how many group up to isomorphism are there for that particular order. So suppose we have given order of group is 1, then the number of group up to isomorphism is only 1. What is that? That is Z1. If order is 2, then Z2. If order is 3, then Z3. If order is 4, then there are two group up to isomorphism. What are those? Those are Z4 and Z2 cross Z2. This is also called K4, that is clean 4 group. And another one is 5, and for that it is Z5. So we can clearly see how many group up to isomorphism are there for a particular order. Now there is remark, if P is a prime, then there is only one group of order P up to isomorphism, namely Z upon Pz, and that is isomorphic to Zp. Another, given any positive integer n, there is a cyclic group of order n, that is Z upon Az isomorphic to Zn. After that, I am talking about a symmetric group, and that is Sn. And what is Sn? Sn is set of isn of on the symbol 1 to n under the composition operation. So here composition will be composition of function, and that is composite operation, you know. So what is composite operation between function, you already know. We already know also. Okay. After that, we will see that order of Sn is nothing but factorial n, because there are n factorial 1, 1 and 2 function between n symbol to n symbol. Now I am talking about a specific example. Suppose 1, 2 belongs to Sn. What does it mean? It means that 1 goes to 2 and 2 goes to 1. And next all I goes to I, where I is different from 1 comma 2. Now, what was the purpose of Galois? I want to see. So for we'll see that Galois was interested in group of commutation of roots of a given polynomial. So suppose we have been given a polynomial, like we have taken px equals x square 4 minus 1, and its roots are 1 minus 1 eta minus eta. So all the commutation of roots gives us s4. We are interested in certain commutation of 1 minus 1 eta minus eta. That is, will deal with subgroup of s4. Will not study whole group as S4, but we will be interested in subgroup of S4 and what are their nature, how do they behave. After that, Cayley theorem, and we already know every finite group is isomorphic to a subgroup of Sn. What is in there? Here there is order of group. He is saying that every finite group can be embedded into Sn. So it is one of the most famous theorem of group theory. What it says that any finite group, whatever maybe its order, it can be made into Sn. That is, Sn has a subgroup which is isomorphic to that finite group. After that, Lagrange theorem, let G is a finite group, and if A belongs to G, that is a age element of G, then order of A divides order of G, that is order of a subgroup divides order of group. It is a backbone of group theory, you know. This theorem is nothing but backbone of group theory. After that, what is subgroup? Here subgroup is nothing but subgroup generated by A, and its order will divide the order of group G. After that, Cauchy theorem, if a prime P divides the order of G, then G contains element of order P. That is, suppose Z8 2 divides 8, then Z8 must contain element of order 2. But 4 divides 8, but 4 is not a prime. 4 is not a prime. Everyone's know. So it doesn't. It is not necessary that Z8 has element of 4. But if a prime P divides, like here it may be that Z8 element of order 4, but in certain other case we will see that if number is not prime, in that case it is not necessary that they will have element of that order. Here Z8 may have element of order 4, but in another case where we will see that, like even you can show Z2 cross Z2. 4 divides group of order 4, but Z2 cross Z2 doesn't have element of order 4. Here this Z8 has element of order 4, but there are certain other groups where uh, since 4 is composite number, 4 divides 4, but Z2 cross Z2 doesn't have element of order 4. Even you know that this group doesn't have even element of order greater than 2. Okay, so this were basic of group theory. It will be helpful in a study of our Galois theory. Okay, thank you.